Alright, last time in 12.2 we did Arithmetic Series. I actually want to review something with that because that helps us set up something for today. So when we had an Arithmetic Series, let's say 5, 7, or sequence, I'll say sequence at this point, but we're going to add them. So 5, 7, 9, 11, and let's say we go up all the way to let's say 31. Okay, now the way we did it last time to actually write a summation with that, right, is that we saw that this was an easy pattern. It was actually linear. So we started with k equals 1, and we said that the change, we looked at the change, which in this case is 2. So 2 would be our slope, and we would have to ask ourselves, what are we adding to it to get to 5, right? If k was 1. So I'm going to replace k with 1, right? And then we solved that out, and we found out that b was 3. So then we would put 2 times k plus 3, and we would have to then solve for k to find that last term. Okay, so I would have 2k equals 28, so k equals 14. We also saw that there were multiple ways that we could write a summation. There might be 2 possibilities, maybe even more. So I wanted to show you one more possibility that actually helps guide us into today's work. So what we actually were finding was when k equals 1, how we could do this. But if you realize though, if we, instead of using k, if we used k minus 1, we now can actually start at our first term. We don't have to solve for b in that case. So we would start with 5 here. And I'll prove that to you right now. If we do 1 minus 1, that's 0. 0 times 2 is 2. 2 plus 5 is 5. So here, just using k, we had to find what's added on to get that first term. But if we use k minus 1, we actually can use that first term. And then I'm actually going to show you now what we can do with finding what term we used last here. So 2 times k minus 1 plus 5 equals 31. So 31 minus 5 is 26. So 2k minus 1 equals 26. K minus 1 is 13. And what do you know? K is still 14. So we have 2 different formulas that we can use to get our pattern. Okay? I'm doing this even though last time I showed you mostly this. We can use k minus 1, and that allows us to use our first term. Either one of these is correct. In today's lesson, 12.3, Geometric Series. Okay, geometric means that we multiply to get to the next term. Okay, that multiplication is called a common ratio. And if you remember from secondary 1, arithmetic meant that it was linear, geometric meant that it was exponential. So we were kind of in a form of b times a to the x. That was our exponential. Okay, now we are doing geometric series, so we are going to use k instead of x, and we're going to see how we can go about with making our formulas. Okay, so let's just write, it says write the series using a sigma notation. So again, we have this summation symbol, okay? This is not one of those, hey, it's right there in your face patterns. So we know we're going to start with k equals 1. And if you look at the change here, what are we doing each time? We are multiplying by 2. So that common ratio is what our base is for our formula. So 2k. Now, well, the easiest thing to do would be able to be using our first term. To use our first term, that would be kind of where y-intercept would be in our normal exponential equation. To use our first term, we must be using not just k, but k minus 1. And I'm going to prove that to you now. If I plug in 1, 1 minus 1 is 0. 2 to the 0. Now you have to remember, anything to the 0 is always the value of 1. And 1 times 1 is 1. So that works. Now we need to use our formula to solve for what term makes 28. So I get 1. Now I'm just keeping the 1 out there, guys, so you realize that that's the first term. Sometimes we forget about that. Times 2 to the k minus 1 equals 128. Okay, so we're looking at 2k to the minus 1 equals 128. And here's where last chapter we did a couple practice with this. Well, we need to change that base. So 2 to the what is 128? 2 to the 7th is 128. So I'm going to put my notes back up here. So I get 2k minus, or 2 to the k minus 1 equals 2 to the 7th. So now I know these exponents must equal. So k minus 1 equals 7, and k equals 8. So I put my ending term right on top. And this is my answer. Okay, so again, it's going to be easier in this case for geometric to use the k minus 1, so we can use that first term instead of going backwards. Okay, so keep that in mind. Using first term, use k minus 1. Alright, so just like in the arithmetic series, we can definitely solve for finite series. So remember that finite means that we have a beginning and an end. We can actually count all the way through it. Now series is a summation of it, so we're actually going to add all of them together. So we're going to go straight to our sum formula. Okay, so we have in this case, it says a, but really it's a subset 1, guys. It's our first term. Okay, r is our ratio and n is the number of terms. So let's see what we have so far. If I plug things in, I have s subset n equals 1 times 1 minus, okay, what's this ratio? What is it going by? It is multiplying by 3. So 3. Do we know how many terms there are yet? No, so I'm just going to put n right now. And then 1 minus r. So we have to figure out how many terms there are, which means we have to go back to our actual formula, just like we did up here, and solve for what term that is. So remember, our formula is going to be our first term times our ratio to the k minus 1, and we are going to set that equal to that last value. We are going to solve. So we get 3k to the minus 1. Let's change our 728 into a different base. So 3 to the 6. Now guys, I had pre-written this out, so all I did on my calculator was like 3 to the 5th, 3 to the 6th, see which ones match. Now that we have the same base, I can now set k minus 1 equals 6, so k equals 7. Alright, that means I can fill this in now. So I have 1 times 1 minus 3 to the 7th all over 1 minus 3. I put r here instead of 3. Okay, well, what does that equal? If you put that in the calculator and press enter, you will get 1093. Alright, in the next one, instead of starting out with the sequence there, we're going to start out in summation form. Okay, so remember what these symbols are. What I want to acknowledge right now is this is k minus 1. So what does that 5 mean? That 5 is that first term, that a subset 1, and that 1/2 is the ratio. Okay, and of course, 10 would be how many terms there are. So let's put them in our formula. So we get S subset n equals 5 times 1 minus 1/2 to the 10th all over 1 minus 1/2. Now when you guys put this in your calculator, let's make sure that you put in parentheses, okay? So I'm going to show you on my calculator right now. So with my numerator, I want to put an extra set of parentheses. So I'm going to say parentheses 5 times parentheses, and it's 1 minus r to the, and then we have 10. So that is the numerator divided by 1 minus 1/2, and enter. Now it's this weird decimal, right? But we want it exact, so make sure you go math, enter, enter, and we get 5,115 all over 512. Alright, so when can we find the sum of an infinite series? Oh wait, I missed page. When I printed it out, my printer does front and back, so let me do this one. Alright, so now we're looking at the idea of an infinite, okay? And remember, an infinite means it goes on forever. So really in your mind you're wondering, how can I add up all the terms that would go on forever? So let's take a look at a couple cases here. Okay. Now what I want you to notice right away, guys, is that this is not k minus 1. This is k. So this is not the first term. What we're going to do right now is we're actually going to plug all of these in our calculator. Sorry, I lost my calculator, guys. Okay. So I'm going to plug it into this equation right here and do each point. So this is what I'm going to do. Remember that this 3 is not the first term here. Okay? And this is the n. So the first term, let's say, we need to plug in 1 first. So 0.1 to the first times 3. So A is actually 0.3. Okay, guys? Now, I'm going to plug this in and I'm going to show you easy how to get all of these quickly. The actual way to do this quickly is to go to your y equals, because we're going to make a table of it. Now, if you don't have a calculator, you can use Desmos, and you can still do a table on Desmos. So, 0.3 times 1 minus, the ratio is 0.1 to the n, but I'm going to put x. Alright, and that's the numerator, divided by 1 minus 0.1. Okay, this allows me to do all these calculations very quickly because I can go second table, and now I have all of my terms. So let's see, when n equals 1, I get 0.3, 2, I get 0.33. So do you guys see a pattern that's happening here? It's almost as if the number, the n, is telling me how many 3's are behind the decimal, right? So on and so forth. And if we ever had to look at this, what do you say about the value that we're finding? Alright, I think I'm done. Because I lost count on my 3's. 1, 2, 3, 4, 5, 6, 7, 8. Craziness. Okay, I'm not going to fill the last 2 in because it's redundant. Okay, so what is happening to the sum as n gets bigger? Well, really, nothing's really changing if we round it, right? I mean, n is getting, the sum is getting bigger, but it approximates to the same value. So what is 0.33333333 repeating, guys? Well, if you look, that means it's going to 1/3. It keeps going closer and closer to 1/3. So let's talk about the ratio. Well, what's the ratio? The ratio is 0.1. 0.1 is less than 1. Okay, that's where I want to go from now. Let's look at the other one. Because if you see, what's the change in the other one here? Well, the ratio is 1.01. Let's find that first term really quickly because remember it changes. So 1.01, calculator, 1.01 to the first times 2, we get 2.02. Okay. Y equals, I'm going to change these things. So I'm going to put in 2.02. Okay, and then I need to put in my new R. I'm doing this where I just put in an insert button, but you guys can rewrite it all over if you want. Minus, and I'll just do 1.01 there. Alright, let's see. Let's go to our table. Let's check. There's our 1. Okay, our next one's 2, so that's 4.062. 6.1208. 8.202. 10.304. So what's happening, guys? What is going on? So instead of filling the rest of these out, let me go to 10 really quick. Look at what that comes out to 21.134. And for fun, let's go to 100. By the way, on a table, if you ever want to go to a specific one, go to second Windows, which is your table set. And I'm going to tell it to start right now at 100 because I want to look at 100. So at 100, it is 344.37. Okay, so let's analyze this, guys. What is happening to the sum as it gets bigger? it's increasing quickly. Right? And the ratio was 1.01, so that's R is greater than 1. Now the thing is, guys, as you can see, this was going all the way and getting very close to 1/3, right? Where this one will keep going on forever, up and up and up and up and up. And could we actually get to a value? All right, let's go on to that next page. So when we find the sum of it, so when can we find the sum? When can we get to an exact value of an infinite series? Okay, well, as we can see, when R was less than 1 for that table, we were able to say, hey, it's getting closer and closer to the actual value of 1/3. But if we looked at the R is 1.01, that summation changed. It kept getting bigger and bigger and bigger. So if you were trying to add from the first term to it going on forever, do we know what value we're going to get? No. So we can only find the sum of an infinite geometric series when R is less than 1. Now, let's be specific on that though. R is less than 1. It means that the absolute value is less than 1. Okay? Because think of this, -2. -2, if we took the absolute value of that, the ratio is actually 2. And then that's going to be greater than 1, and we're not going to be able to count that infinite series. So, let's move on. These are the only ways that we can find the value. Excuse me, guys. And this is going to actually be our formula to help us find what the value of that infinite series is. Okay, so here's some vocabulary for you. We can only use this formula when the series converges. Converges means that the absolute value R is less than 1. Otherwise, we say the series diverges, and we can't find the sum. I'm going to show you graphically what that kind of looks like. Okay, remember when we have our asymptote, guys? The part of our equation that gets very close to that asymptote and it keeps getting closer and closer, that is the part that converges. Because it's converging, it's getting closer and closer to that asymptote. Where on the other side here, as we go this way, it's going out to every value possible, so that diverges. It's getting farther and farther away. Okay, so that's what it means if you were to put a picture to it. So the first thing we have to do is find out if the series converges or diverges. Because once it diverges, we're done. We can't find it. But if it converges, then we can find the summation. Okay. So what is happening each time here? Well, if you look, the numerator is multiplying by 5 and the denominator is multiplying by 6. So you tell me the absolute value of 5, 6. Is that going to be less than or greater than R? Well, it's less than 1, so it's going to be less than. And I don't mean R, I mean 1. Sorry, guys. Very good. So this converges, which means we can definitely find the summation. Okay? But this is just determine if it's converging or diverging. Okay, let's look at the next one. The ratio here is 4 over pi. So it's the absolute value, just in case that negative was in there. And we have to say 4 over pi, is that going to be greater than 1 or less than 1? Well, pi is 3.14, blah, blah, blah. And 4 is greater than that, so it's going to be greater than 1, which means it diverges. and we can do nothing beyond that point. All right, 2 more problems, guys. Find the sum of the infinite geometric series. I want you guys to get in the habit of testing if it's converging first, because then you'd be doing all that work for nothing. So let's check what's going on. Ooh, this is a new pattern, guys. What's happening between the minus and the plus? We're changing signs there, which means we're multiplying by a negative number. Okay, the numerator stays 1, so the only thing multiplied there is 1. But what's going on the bottom? 2, 4, 8, 16. We are multiplying by 2. So R is negative 1/2. Okay, let me write down that formula we are using for the sum. Remember that A is the first term, and R is the ratio. Sorry that it's not. That work? Okay, so as this is focusing, so negative 1/2. Well, the absolute value of negative 1/2 is 1/2, and that would be less than 1. So we know it converges, so we can do this. And we're going to put this in the sum equals, well, the first term is 1/2, and the ratio is negative 1/2. So that means that our summation, let's look at our calculator, do this. Don't forget you want to have parentheses around that 1/2. I forgot the 1. Divided by 1 minus negative 1/2 equals 0.3333. What is that, guys? That is 1/3. Just like in our table. Right? Let's check the other one. Our ratio is 1/pi. Well, that is definitely less than 1, so it's converging. Awesome. So let's put it in our formula. The first term, be careful here, because what is the first term? This is k. This is not k minus 1, so this is not the first term, guys. So we must plug in to find that first term. So we have 5 times 1/pi to the first. Okay, so what do you know? That's 5/pi. I'm going to do that so we're not approximating in the middle of a problem. So the first term is 5/pi all over 1 minus 1/pi. Alright, now I'm actually going to put this in our calculator and check that out. So 5 divided by pi divided by 1 minus 1 divided by pi equals that. Let's see. No, it's probably not. So guys, we could actually make this into a simpler form instead of using decimals, but I'm going to show you so that way you can see. Let's see. So on the bottom I would need common denominators, so 5 pi over pi minus 1/pi. Okay. Then I'm actually going to grab another sheet of paper, that way we can do the work on there. Okay. That would mean, so I'm going to go over here, guys, so I can continue and show you how to do that. We have 5 pi all over pi minus 1/pi. Well, what do we do when we divide by a fraction? We multiply by its reciprocal. So pi over pi minus 1. Okay, these two pi's cancel, and we are left with 5 over pi minus 1. Okay, so that is our answer. And I'm going to prove to you that that is the same amount. So 5 divided by pi minus 1. And what do you know? Same value. Okay, this is just more accurate because it's exact, whereas if we put in the 0.2, 3, 3, 4, we're approximating it. So it depends on your teacher and the question if they're okay with you approximating. One thing I'm going to point out before I leave you right now is that when we write a summation form of infinite series, as you can see on the top is the infinity symbol because we do not stop. So this is how it would look for an infinite series.